As we all know, antennas play a crucial role in communication using EM waves. But we face some problems that drastically reduce the performance of antennas. The length of antennas must be at least the order of the wavelength for practical communication. Conventional antennas that are very small compared to the wavelength reflect most of the signal back to the source. A metamaterial antenna behaves as if it were very much larger than its actual size because of its novel structure, stores and re-radiates energy. Hello everyone. Today we are going to discuss electromagnetic metamaterials, and towards the end of the video we may throw some light on how metamaterials make communication with much reduced antennas possible. Almost all materials encountered in optics, such as glass or water, have positive values for both permittivity epsilon and permeability mu. However, metals such as silver and gold have negative permittivity at shorter wavelengths. But metamaterials, as they are called, can be engineered to have properties not found in nature, that is, exhibit negative permittivity as well as negative permeability at the same time. An electromagnetic metamaterial affects electromagnetic waves incident on it via structural features; those are smaller than the wavelength of the respective electromagnetic wave.
Refractive index of a material is given by the under root of the permittivity epsilon and permeability mu. When both epsilon and mu are positive, the refractive index is taken as the positive square root. If exclusively one is negative, as in the case of surface plasmons, the square roots are imaginary and the material is opaque. But for metamaterials, both epsilon and mu are negative, and hence the negative square root for refractive index must be taken. Negative refractive index can sound very bizarre. Snell's law predicts that during refraction, the rays should get refracted on the same side of the normal on entering the metamaterial. Also, instead of following the right-handed rule, metamaterials follow the left-handed rule. These amazing properties of metamaterials can have surprising applications. Electromagnetic metamaterials find uses in absorbers, superlens, cloaking devices, seismic protection, and antennas, which we had promised to discuss at the beginning of the video. Antenna designs incorporating metamaterials can step up the radiated power of an antenna. Standard antennas need to be at least half the size of the signal wavelength to operate efficiently. At 300 MHz, for instance, an antenna would need to be half a meter long. In contrast, experimental metamaterial antennas are as small as 1/50th of a wavelength. Metamaterials have revolutionized electromagnetic communication by their amazing property of negative refractive index, and it is interesting to note that some of the earliest structures that may be considered metamaterials date back to Jagdish Chandra Bose, who in 1898 researched substances with chiral properties. Thank you.